just like sample problem 3.15, sample problem 3.16 also builds off of the previous problem. So again, before I read the problem, let's go ahead and write down the balanced equation that we've been talking about, and it was for the two copper sulfides. Oh, sorry, that doesn't look like a 2 at all. 2 copper sulfides plus 3 oxygens yields 2 copper oxides plus 2 sulfur dioxides. And so this problem is giving us the kilograms. Well, let's just read it first. During the roasting of copper 1 sulfide, how many kilograms of oxygen are required to form 2.86 kilograms of copper 1 oxide? So again, they're giving us information about one thing, right, copper 1 oxide, and they're asking us information about something totally different, kilograms of oxygen. Balanced equation is the only conversion factor that can relate two different things to each other. So, I know that I have 2.86 kilograms of copper oxide. Now, remember, the stoichiometric coefficients from the balanced equation tell me moles, right? So for every 2 moles of copper oxide, right, it requires 3 moles of oxygen. So before I can answer the question about oxygen and use this balanced equation for my conversion factor, I have to get this into moles, right? I have to somehow convert my kilograms into moles. What relates mass to moles? Again, molar mass from the periodic table, remember? And those units on the periodic table are in grams per mole. Key thing there being grams, and here we have kilograms. So the first thing I got to do is convert these kilograms to grams. And we all know from chapter 1 that in 1 kilogram, so that's got to go in the bottom because I'm starting out with it in the top, there are 1,000 grams. And now I can use my molar mass from the periodic table to get from grams to moles. So let's see, I've got 2 coppers, so 2 times the molar mass of copper from the periodic table, which is 63.55, plus 1 oxygen, which is 16 grams per mole from the periodic table, is 143.1. So 143.1 grams of copper oxide in 1 mole of copper oxide. So let's see here. Let me check my units. I've got kilograms divided by kilograms. They cancel because that's equal to 1. I've got grams divided by grams. They cancel because that's equal to 1. So these are my units, right? This moles of copper 2 oxide. That's what I'm going for so that I can use these stoichiometric coefficients here in the balanced equation to convert from one thing to something totally different. So let's do our math now. What's this equal to? 2.86 times 1,000 divided by 143.1 equals, and I got 19.99 moles of copper oxide. All right, so let's rewrite that down here. 19.99 moles of copper oxide. And set up our T. From the balanced equation, I can now go from moles of copper oxide to moles of oxygen. So let's see, for every 2 moles of copper oxide, so let's write that in the bottom because that's what's in the top is copper oxide. I use 3 moles of oxygen. All right, and so what's that going to be equal to? So times 3 divided by 2 equals, so I got 29.98 moles of oxygen are required. But the problem's asking for kilograms, so I've got to relate moles to mass. And just as it was before, whenever I was doing the copper oxide, the molar mass is what relates grams to moles and moles to grams. So 29.98 moles of oxygen, and I'm going to set up my T. Now the molar mass of O2, that's 2 times 16, right? Because the molar mass of oxygen is 16 grams per moles from the periodic table. So 2 times 16 would be 30, oh, I'm writing that in the wrong spot. 32 grams of oxygen in 1 mole of O2. All right, so let's check our units. I've got moles divided by moles, and I'm going to be left in grams. But I'm going to keep going with this because they want this in kilograms. And we know that there are 1,000 grams in 1 kilogram. And so let's check. I've got grams divided by grams, which equals 1. They're going to cancel. So what is this equal to? 29.98 times 32 divided by 1,000 equals 0.959 kilograms of O2 are going to be required to form 2.86 kilograms of the copper 1 oxide to answer the question.